Hello, and welcome back to Homework Help for Math 2. Today we're going to be looking at Chapter 6, Trigonometry, Lesson 2, Right Triangle Trigonometry. We'll go ahead and get started with question number 1. Questions 1 through, well, it's actually 1 through 2, not 1 through 3. For numbers 1 through 2, write the indicated trig ratios, not rations. If any sides of the triangle are missing, find them before determining the ratio. So, number 1. In this problem, we are given all three sides, so we do not need to find any of the missing sides. We can kind of just jump right into finding these ratios. So what I'm going to do is I'm going to go ahead and I'm going to go and fill in all of the ones dealing with angle A first. So we're going to be dealing with this guy, and this guy, and then we'll deal with angle B. So if we're talking about angle A, which is right here, well, 8.06 is my hypotenuse no matter which angle I'm talking about, right? 8.06 is the hypotenuse, and it doesn't really change. Now, because we're starting by talking about angle A, well, that means that if I go, opposite like this, it means that the 7 is my opposite, and then adjacent is my 4. Now I just need to remember what my definitions are in a right triangle for cosine, sine, and tangent. So cosine is, you think, toa, and cosine is adjacent over hypotenuse. That's the definition of cosine in a right triangle. So we've already labeled the 4 as my adjacent, and my hypotenuse is 8.06, and that's my answer. That is the ratio of the adjacent side to the hypotenuse for angle A. Sine, which is right here, is opposite over hypotenuse. Again, that's the definition of the sine function in a right triangle. Opposite is 7, and the hypotenuse doesn't change. It's 8.06. Then there's tangent, toa. So the definition for tangent is opposite over adjacent. For angle A, my opposite is 7, and my adjacent is 4. And that is my tangent ratio for angle A. So we've now done all of the questions dealing with angle A. Now let's look at the same thing, but for angle B. Like I said, the hypotenuse doesn't change, right? So 8.06 is most assuredly still my hypotenuse. But now that we're talking about angle B, well, now opposite is the 4, because that's the side, that's the leg that is opposite angle B, and then the leg that is adjacent is the 7. My definitions do not change. So the definition of cosine in a right triangle is adjacent over hypotenuse. So now my adjacent is 7, and my hypotenuse, as always in this problem, is 8.06. The definition for sine doesn't change. It's opposite over hypotenuse. Now my opposite is 4. My hypotenuse is 8.06, and that's my sine ratio. Tangent, as always in a right triangle, is opposite over adjacent. This time opposite is 4, and my adjacent is 7. And so that is it for question 1. I would encourage you to pause for a second and to sort of try to identify any patterns that you may notice in this problem. So between all 6 of these ratios, See if you can identify any patterns between, sine, cosine, and tangent for both angles A and B, because there's definitely some things going on there, and I'm not going to spell them out for you, but you might be able to identify some relationships between the trig functions and the various angles. Question 2. Question 2 says it's the same thing, and we are given all three side lengths. So again, I don't need to find a side length here. I can just jump right into my trig ratios. This one I'm going to do a little bit quicker than number 1. So cosine, the definition for cosine, as always, is adjacent over hypotenuse. I'm going to do all of my angle A's first. So 9.01 is always the hypotenuse, regardless of what you're talking about. And for angle A, 3 is opposite, and 8.5 is adjacent. Like I said, the definition for cosine, that's ca, so it's C-A-H, so it's adjacent over hypotenuse. Adjacent in this case is 8.5, and my hypotenuse is 9.01. The definition for sine is opposite over hypotenuse. So we've labeled 3 as opposite, and 9.01 is my hypotenuse. And then tangent is opposite over adjacent in a right triangle, and so opposite is 3, and adjacent is 8.5. Now that we're talking about angle B over here on the right, I can keep hypotenuse labeled the same thing because, again, it doesn't really matter which angle you're talking about. The hypotenuse doesn't change. But now if we're talking about angle B, well, now 8.5 becomes opposite, and the 3 becomes adjacent. Definition for cosine is adjacent over hypotenuse, and so that becomes 3 over 9.01. Definition for sine is opposite over hypotenuse, and so that is 8.5 over 9.01. And then the definition for tangent is opposite over adjacent, which is 8.5 over 3. And again, just like in problem 1, I would encourage you to pause for a second and see if you can identify any patterns that exist between the trig ratios and the different angles. If you had a conjecture about the pattern in number 1, I would encourage you now to check your conjecture and see if the same pattern that you identified in number 1 holds up in number 2. Question number 3. Directions here say for problems 3 and 4, use the given right triangle to identify the trigonometric ratios and angles. All right. So for number 3, we have 2 of our sides. Specifically, we have both of our legs. However, we are missing our hypotenuse. Now, as a quick side note here, notice that both of my legs are congruent, which means that this is an isosceles right triangle. And in an isosceles right triangle, which is also known as a 45-45-90 triangle, right? Those two terms are essentially synonymous. There is a certain pattern that exists, and if you know that pattern, you could actually jump immediately to your hypotenuse. However, I'm just going to assume that people don't know that pattern. And so I'm going to go ahead and actually do the grunt work in order to identify what the hypotenuse is. But when we're done, I just would like to point out that there is a certain pattern that exists with isosceles right triangles, where if you know the leg or legs, you know the hypotenuse, and then vice versa. So if you don't know what else to do, when you are given a right triangle and you have 2 of the sides and you are looking for the third side, you can always use the Pythagorean theorem. The Pythagorean theorem, as always, says that the sum of the squares of the legs of a right triangle is equal to the square of the hypotenuse. And again, I would encourage you to not get locked into the A, the B, and the C, because notice that in this triangle, we also have A, B's, and C's. Now, it actually does work out that, like, this is A, this is B, and this is C. But that's just kind of arbitrary. I mean, you could label the triangle with any letters that you want, and so you really don't want to get locked into the A, the B, and the C. What you want to get locked into is the fact that the legs are on one side of the equal sign and that the hypotenuse is on the other side of the equal sign, regardless of what letters, sort of are involved in a specific problem. So one of my legs is 1, so 1 squared. My other leg is also 1. That's what makes it isosceles. And then we don't know our hypotenuse, so we leave it like that. I like to move the thing that I'm solving for to the left, so this becomes c squared. 1 squared is 1, and 1 squared is also 1, and 1 plus 1 is 2. So c squared is 2. I want to get c by itself, so we'll take the square root. And when I do that, I get rid of the squared, so I have c. And as I've said before, you do not need a plus minus here because we're talking about the length of a triangle. And so even though sort of the algebraic rule is that you would normally need a plus minus root 2 here, we can drop the plus minus and deal strictly with the positive one because c is clearly a positive number. Right? Negative root 2 would not make sense in this context. So we do not need the plus minus, and so therefore c is root 2. Just like that. And that is, now we've solved for all three sides. And so now what we can do is we can go ahead and find our trig ratios. Again, I'm going to stick with one angle at a time. So we'll go ahead and we'll start with angle A. Root 2 is my hypotenuse, no matter what. And then if we're talking about angle A, well, it means that this is opposite, the side A, which is 1. And then side B, which also happens to be 1, is adjacent. So sine, as always, in a right triangle, the definition for sine is opposite over hypotenuse. So opposite is 1. And my hypotenuse is root 2. Now, depending on your teacher and sort of what they're expecting from you, this may or may not be your final answer because this is correct, except one thing that mathematicians don't really like is having a square root in the denominator of a fraction. We just don't like it for reasons that, if you're curious, maybe we can talk in person. But suffice to say, it's generally not good practice to leave the square root in the denominator. So if your teacher cares about this or sort of wants you to change it, that's just kind of an individual thing. So if your teacher doesn't care, then this is your final answer. However, if you want to kind of take the extra step and do what's called rationalizing the denominator, what we do is we multiply by the number 1, but we write the number in kind of a weird way, and we write it as the root 2 over root 2. Now, hopefully, people recognize that this is, in fact, the number 1, because anything over itself is 1, other than 0. But root 2 over root 2 is 1. And so what we're doing here is we're multiplying by 1, and so we're not changing the value. We're just sort of like, we're rationalizing the denominator is what we're doing. So if you go and you multiply your numerators, well, 1 times root 2 is root 2. And then the denominators, root 2 times root 2, well, your square roots go away and you're left with just 2. So again, depending on what your teacher is looking for, I would say either 1 over root 2 or even better is root 2 over 2. It's a good habit to get into. And so I would encourage you to actually give the, quote, better answer. But if you were able to get at least 1 over root 2, that's pretty good. Let's deal with cosine. So the definition for cosine in a right triangle is adjacent over hypotenuse. And so my adjacent is 1, and my hypotenuse is root 2. Well, notice that it's actually identical to sine. And so by the very same reason, I mean, it's the same number, so it's got to also be root 2 over 2, right? I mean, it's the same thing, so you could rationalize it the same exact way and get the same answer. I don't know why it made that box. Let's try that again. Why is it? We're going to try this one more time, and if it doesn't work this time, I'm going to give up. Make a nice box. Okay, whatever, that's good enough. So cosine of A is either 1 over root 2, or even better, the better answer is root 2 over 2. Tangent. Definition for tangent in a right triangle is opposite over adjacent. My opposite is 1, and my adjacent is 1. Well, 1 over 1, again, anything over itself other than 0 is 1. And so 1 divided by 1 is most assuredly 1. And so let's write our answer, a little bit nicer than 1 over 1. It's kind of strange. And just leave it as 1. So the tangent of A is 1. Now let's deal with B. So we're dealing with B. So that changes. And now we're dealing with this angle here. So now that we're dealing with angle B, well, then side B is opposite. And side A is adjacent. And sine, as always in a right triangle, is opposite over hypotenuse. Well, my opposite is 1, and my hypotenuse is root 2. And I got it again. I got the same thing that I got for sine of A and cosine of A. I again get 1 over root 2. And so by the same reasoning, this is also root 2 over 2. And so those are, or that is my answer, depending on how you're sort of expected to write it. Some of you might see already what's going to happen with cosine of B, but in case you don't, cosine, as always, in a right triangle is adjacent, which is 1, over my hypotenuse, which is root 2, and again, I get the same thing. So by the same reasoning, we get root 2 over 2, and the answer on the left is okay. The answer on the right is even better. So I'll just sort of maybe highlight the quote better answers here. But again, as long as you're able to get 1 over root 2 to start, you're in good you're in on the right track. We'll say it that way. Tangent of B, well, tangent is opposite over adjacent, and 1 over 1 is still 1, and so we also get 1 for tangent of B, and that is question number 3. Question number 4. Now, question number 4 might look scary to some people because there's no numbers. I mean, I guess technically there's 90 degrees, but other than the 90 degrees, there's no numbers. We just got letters all over the place. And so people might look at this and they might get a little intimidated or scared. But it actually turns out that 4 is easier than it looks, because if you don't have any numbers and all you have is letters, well, you don't even have to worry about like simplifying or rationalizing, or, you just plug in. We're just going to be plugging in like X, Y, and Z, and then whatever our answers are, that's it. There's no simplification. There's no rationalization. You just write it and you move on. So we're going to, as always, we're going to focus on one angle at a time. So we'll start with angle A. So that's angle A, right there. Z is my hypotenuse no matter what. X is my opposite, and Y is my adjacent. Sine in a right triangle is opposite over hypotenuse, so that is X over Z. And that's it. There's nothing I can do with that. There's just 2 letters, and that's my answer. Cosine, as always, is adjacent over hypotenuse, and so that is Y over Z. And again, there's nothing I can do with that. That's my answer. Tangent is opposite over adjacent, and so that is X over Y. And that's my answer. Moving over to angle B, so we'll get rid of that, get rid of that, get rid of that. We're now talking about angle B. Because we're talking about angle B, it means that Y is now opposite and that X is adjacent. Those 2 things swap. Sine, as always in a right triangle, is opposite over hypotenuse, and so that's going to be Y over Z. Cosine, as always, is adjacent over hypotenuse, and so that's going to be x over z. And then tangent is, as always, opposite over adjacent, and so that is y over x. And that's it for number 4. As I said earlier, if you have noticed any patterns here between sine, cosine, and tangent of my two angles, once again, check and see, is your conjecture correct about sort of the pattern that follows these three trig functions with the two angles? And if you haven't yet identified a pattern, I would encourage you, again, to take a second, pause, and see if you can identify a pattern between sine, cosine, and tangent between my two angles here, A and B. Question 5. Well, 5, 6, and 7. For numbers 5 through 7, based on the given trig ratio, sketch a triangle and find a possible value for the missing side as well as the other missing trig ratios. Label angles A and B as the two non-right angles in the right triangle. It says non-right angles. I mean, they're going to be acute angles because in a right triangle, you have one right angle and two acute angles. So not only are they non-right, but they're also acute specifically. There's no obtuse angles here. So the first thing they want us to do is to sketch. Now, I would encourage you to not stress too much about whether your sketch is to scale. I mean, if you feel like you can draw it to scale, then by all means do so. But if you feel like you're not really sure, sort of like, does this triangle, does it look like maybe like short and long, or is it sort of like almost isosceles, or if you can't sort of visualize it in your head, then I would just sketch just a right triangle, regardless of whether it's to scale, and then just label the numbers, and then just remember that your triangle might not be to scale, right? I'm going to try to draw mine relatively to scale. And so the information that we're given here is we are told that the tangent of A is 3/4. Now, please remember that this 3/4 is a ratio, right? So it's 3/4, which is also the same thing as 6/8, which is also the same thing as 9/12, and so on, right? And you can have decimals, you could have, all sorts of stuff here. And so we're going to use the 3/4, but please do remember that it's a ratio, and so we don't actually know what the side lengths are. We just sort of know how they relate to each other. So when I draw this triangle, I'll do the sketch down here, it turns out that this triangle looks kind of like this. All right, that's a roughly to scale triangle. Maybe the bottom should be done a little bit longer, but it's fine. So there's my right angle. And if I'm gonna, it doesn't really matter where you put A and B, unless you want your picture to be to scale. If I want this picture to be to scale, then A kind of has to go there and B kind of has to go there. If you were to flip them around, that's not wrong. It just means that, again, your picture's not to scale, and so you just can't really trust, how it looks versus the numbers that you're dealing with. C does have to be the right angle according to the directions. So C does have to be where our right angle is located. All right, so we have our sketch. Now, again, the information that we're told is that the tangent of A, which is right there, the tangent of A is 3/4. Well, the definition for tangent is opposite over adjacent. And if we're talking about angle A, then this is always my hypotenuse, regardless of what angle we're talking about. And then this side would be opposite angle A, and this side would be adjacent angle A. And we know that the ratio of opposite to adjacent in this triangle is 3/4. So what that means is you could do 3 and 4. Now, like I said, what matters here is the relationship between them, not the numbers themselves. And so theoretically, if you were to label this as 6 and label this as 8, that is also correct. So because the ratio of the sides is 3/4, even though the numbers themselves are 6/8. 6/8 simplifies to 3/4. Likewise, 9/12 simplifies to 3/4. So what matters here is that your side lengths have the correct ratio But as long as the ratio is correct, the numbers could really be almost anything. Again, as long as they relate to each other in the correct way. Now, we're not going to use the 6 and the 8. We're going to stick with the 3 and the 4. I just wanted to make sure that people understood that this 3/4 does not mean that your opposite must be 3 and that your adjacent must be 4. They just have to sort of relate to each other in that way. All right, so we have 2 of our sides, but we don't have our hypotenuse. And we know that we're going to need all 3 sides to fill in sine, cosine, and tangent. So let's go ahead and find our missing side. We'll call it, because it's across from angle C, we'll call it side C. And anytime you have a right triangle and you know 2 sides and you want the 3rd side, we can use the Pythagorean theorem. So the Pythagorean theorem, as always, says that the sum of the squares of the legs of a right triangle is equal to the square of the hypotenuse. And one of our legs, in this case, is 3. Another leg is 4. And our hypotenuse is the thing that we don't know, so that's going to be C. So we leave that there. We flip it around. 3 squared is 9. 4 squared is 16. 9 plus 16 is 25. I want to get C by itself, so I take the square root. And so C equals, and because I know I'm finding a side length, I do not need my plus minus because negative does not make sense in this context. So it's strictly positive, and the square root of 25 is a nice round number, which is 5. And so I'll replace my C with a 5. Notice that 3, 4, 5 is a Pythagorean triple. So if you're able to recognize your Pythagorean triples, when you see the 3 and the 4, you could potentially just skip right to the hypotenuse and just say that, well, I know that 3, 4, 5 is a Pythagorean triple, so that the hypotenuse has to be 5. But if you're not yet noticing the Pythagorean triples, you can always fall back on just doing the Pythagorean theorem, and you'll get the 5 as opposed to just like looking at it and knowing that it's 5. However, I think for this problem, if you recognize the Pythagorean triple, I think it's sufficient to just write it. Unless the directions say use the Pythagorean theorem specifically, or unless your teacher says you must use the Pythagorean theorem. With a problem like this, if you can recognize the triple, I think it's fine just to go ahead and put the 5, because the directions don't specifically say that we have to use the Pythagorean theorem. All right, so we're focusing on angle A to start. We already know tangent. The sine of A, well, sine is opposite over hypotenuse, and my sine, I covered up the 3 a little bit, but it is in fact a 3. So it's 3, and then my hypotenuse is 5. Cosine in a right triangle is adjacent over hypotenuse, and so this is 4 over 5. That's it for angle A. Okay. Now we're looking at angle B. My hypotenuse doesn't change. 4 becomes my opposite, and 3 becomes my adjacent. Definition for tangent in a right triangle is opposite over adjacent, so that's going to be 4 over 3. Sine is opposite over hypotenuse, so that's 4 over 5. And cosine in a right triangle is adjacent over hypotenuse, which is 3 over 5. And yet again, I would encourage everyone watching this video right now to check and see these patterns between sine, cosine, and tangent for the 2 different angles. At this point, I'm really kind of hoping that people are starting to notice the pattern between these 6 entries. And if you do not yet see it, take another look at it and see if you can figure out how these various ratios relate to each other. Question 6. The directions ask us to sketch the triangle. Like I said, for 5, if you feel like you can't really visualize this triangle in your head and you're kind of worried about it being to scale, don't worry about that too much. As long as the numbers and the letters are in the right place, it doesn't technically matter if the triangle is to scale or not. I am going to try to draw this triangle to scale. And so let me think for a second. All right, so we have a triangle that looks like this. With a right angle right there. And I'm going to go ahead, I'm going to put my A there, my B there, and my C there. Again, if you're, I'll make that that looks like a lowercase c. Make that a capital C. If the sketch of your triangle looks, dramatically different than mine, it's really not that big of a deal. It does have to be a right triangle, so that's you can't change that. You need a right triangle. But if your right triangle looks, markedly different than mine, don't worry too much about it. I'm just trying to draw mine to scale, given the piece of information that we're given, which specifically, I should say, is this piece right here. We are told that the sine of b is 8 over 17. And as I mentioned in the last problem, this is a ratio, which is also the same thing as like 16 over 34, or 24 over 51. Yep. And there's an infinite number of ratios that are equivalent to 8 over 17. So the 8 over 17, it doesn't really tell you what the side lengths of this triangle are. All it tells you is how they relate to each other. But we're going to keep it simple, and we're just going to use the 8 and the 17 because there's really no reason not to. So the definition for sine in a right triangle is opposite over hypotenuse. So if we're talking about angle B, which is right here, my hypotenuse, as always, is across on the right angle. For angle B, this is my opposite at the bottom, and then going over here on the left is my adjacent. Like I said, the definition for sine is opposite over hypotenuse, and so I'm going to label my opposite as 8 and my hypotenuse as 17. Technically, I could have done 16 and 34. I could have done 24 and 51 because all three of those pairs have the same ratio of 8 to 17. I know that I am going to need my other side eventually. And so what we have here is we have a right triangle where I know two of my sides and I'm missing my third side. And that is a prime example of where I want to use my Pythagorean theorem, or the Pythagorean theorem. So the Pythagorean theorem, as always, says that the sum of the squares of the legs of a right triangle is equal to the square of the hypotenuse. Based on my picture, I'm looking for side A, so I'll leave that where it is. Side B, which is across from angle B, we labeled it as 8. And then C, which is the side across from angle C, which is a right angle, which means it's the hypotenuse, we've labeled it as 17. Now I want to get A by itself. Now the step that I'm about to do is technically not strictly necessary. You could theoretically skip this step, but I do find it helpful to simply evaluate the squareds. It just makes things a little bit easier, and you could skip it if you wanted to, but I recommend you just go ahead and just fill in what these numbers are. So 8 squared is 64, and 17 squared, I always get this, I think it's, 289? Yeah, 289. All right, so 289. I want to get A by itself, so we're going to subtract 64, that cancels, and so we've got A squared equals 289 minus 64 is 225. I want to get A by itself, so I take the square root. A equals, we do not need the plus minus because we're talking about the length of a triangle, side length of a triangle, and the square root of 225 is 15. So I'm going to label this as 15. And we now have all the information we need in order to finish out this problem. We're already talking about angle B, so we might as well finish out the ones dealing with angle B first before we change our labels. The definition for tangent in a right triangle is opposite over adjacent. Opposite in this case is 8, and adjacent is 15. Definition for cosine in a right triangle is adjacent over hypotenuse. My adjacent is 15, and my hypotenuse is 17. We'll jump over to angle A. So angle A. My hypotenuse doesn't change. However, now 15 is my opposite and 8 is my adjacent. The definition for tangent in a right triangle is opposite over adjacent, and so that is 15 over 8. Definition for sine is opposite over hypotenuse, which is 15 over 17. And the definition for cosine is adjacent over hypotenuse, and based on how we've labeled our triangle, that is going to be 8 over 17. And that's it for question 6. Check your conjecture, make sure it still works with these 6 answers. Question number 7. Again, we will start by sketching. So, got that. All right, hold on, that seems slanted. Let me do that one more time. All right, there we go. Let me do that. I'm being perfectionist right now. Give me 1 second. That's good. Again, I'm trying to draw mine to scale. If you just slap a right triangle on the page, and as long as your numbers and letters are correct, it doesn't necessarily need to be to scale. So my triangle looks like this, and we need to label. We'll go ahead and just say A, B, and C. Now, notice that this time the information that is given, they actually gave it to us in a non-rationalized form, which actually makes our job a little bit easier. I do just want to point out, however, that it's a good idea to recognize that if you do rationalize this, you end up getting root 2 over 2. And that's a value that when you're working in trig, you're going to see that value a lot, root 2 over 2, but we'll get to that later. But anyway, we're going to stick with the 1 over root 2 because that's the information that they gave us. So we're talking about angle B. So angle B. Side C is my hypotenuse, always. The information that we're given deals with sine. The definition for sine is opposite over hypotenuse. And so if we're talking about angle B, then this is opposite and this is adjacent. Like I said, sine is opposite over hypotenuse, and so opposite is going to be 1, and my hypotenuse is going to be root 2. Now, you may recognize this triangle from an earlier problem in this assignment. However, if you didn't do that problem, or if your short-term memory is, maybe not so good, I'll show you how to do this using the Pythagorean theorem. But again, this triangle, we've already seen this triangle before in an earlier problem. But if you don't recognize it, you can always fall back on the Pythagorean theorem because, again, we have a right triangle here, and we know 2 sides, and we're solving for the third side. So that's just like a classic Pythagorean theorem question. Pythagorean theorem says that the sum of the squares of the legs of a right triangle is equal to the square of the hypotenuse. I guess technically in this picture, it's side A that we don't know, so I'll leave the A in there. Doesn't really matter if you plug in for A or B. It really doesn't matter. The leg that I do know is 1, and my hypotenuse is the square root of 2. I would recommend that you actually evaluate these squareds. So we end up getting a squared plus 1 squared is 1. And the square root of 2 squared, well, the square root and the square root cancel, and you're left with just 2. But please don't make the mistake of doing 2 squared and getting 4, because that's not what we're doing. We're not squaring 2, we're squaring the square root of 2. And so the squared and the square root cancel. We're going to try to get a by itself, so we subtract 1 from both sides. And so a squared equals 1. I take the square root of both sides, And that leaves me with just a. We don't need our plus minus because we're talking about side length. And the square root of 1 is simply 1. And so a is 1. We'll stick with angle B because we've already started with angle B. The definition for tangent in a right triangle is opposite over adjacent. So opposite is 1, adjacent is 1. 1 divided by 1 is 1 because any non-zero value divided by itself is 1. Definition for cosine is adjacent over hypotenuse, and my adjacent is 1, and my hypotenuse is root 2. Now, I would say for this problem, because they gave you 1 over root 2, I would say you're pretty safe staying with just 1 over root 2, right? If you sort of are a little extra and you write this as root 2 over 2, that's great, and that is absolutely correct. And I would say it's even better. But because they're giving you the information in an unrationalized form of 1 over root 2, I'd say in this situation, if you leave it as 1 over root 2, that's also fine, because they can't really expect you to, rationalize it if they don't even give the information to you in a rationalized form. So root 2 over 2 is better, but 1 over root 2 is fine as well. We'll switch over to angle A. Root 2 stays as my hypotenuse, but now that we're talking about angle A, it means that this side is opposite and this side is adjacent. And you can probably tell already that it's not really going to matter because they're both 1, right? So we're going to see a lot of repeats here. Tangent is opposite over adjacent. Opposite is 1, adjacent is 1. 1 divided by 1 is 1. Sine is opposite over hypotenuse, and so that's 1 over root 2, which, if you want to be extra, you could say is root 2 over 2. And cosine's adjacent over hypotenuse, which is also root 2 over 2. And yep, I'd say that should be. Now you should not leave tangent as 1 over 1, right? So that's a simplification that you're really you really should do. Don't leave it as 1 over 1. You should say 1. But for all of these other ones, if you leave it as 1 over root 2 for this problem, because they gave it to you in that form, I think it's fine to leave it in that form if you want. All right, questions 8 through 10. For 8 through 10, given a right triangle with angles A and B as the non-right angles, or the acute angles, determine if the statements are true or false. Justify your reasoning and show your argument. All right. I want to underline this sentence here. And I'm going to highlight it too. Right. I feel like sometimes students, I don't know if they deliberately ignore that statement or they just genuinely just skip over it or whatever. With a true-false question, you got a 50% chance of being right if you just guess, right? It's either true or it's false, and that's it. So with a true-false question, you really kind of got to back it up a little bit, right? So if all you said was true or false, but you didn't have anything else on your paper, that's not good. Right? The directions specifically say justify your reasoning and show your argument. So you can't just say true or false. You have to have a little bit extra here in order to get full credit. If you put true or false with no backup, I guess maybe that's a 2, right? Because I guess you're on the right track as long as you're correct. But I don't think you'd get a 3 or a 4 if you put the right answer, but you don't back it up, right? And you want to go for more than a 2, right? Don't settle for a 2. You should go for a 3 or a 4. So, and maybe it's a 1. I don't know. Maybe it depends on your teacher. So, if you don't know what to do, if you don't know how to sort of back it up or whatever, you can start by maybe doing a sketch. So that looks. I don't know why that looks. Maybe that's not crooked, but it looks crooked to me. All right. So if you don't know what to do with a problem like this, try sketching it. Maybe this will be helpful. Maybe it won't. Right? I don't really know. And we'll just label this as any old thing, A, B, and C. And notice that for number 8, we're dealing pretty much exclusively with angle A, right? We're saying, all right, cosine of A is equal to 1 over the sine of A. And also notice that this is another way of saying the reciprocal of sine of A, right? So if the sine of A is like, let's say 3/4, it means that 1 over 3/4 is 4/3, right? You flip the fraction. This isn't just, it's just the reciprocal. So we're talking about angle A here. So in my picture, that's my hypotenuse. This is my opposite, and this is my adjacent. And so this is asking, is this true or false where the cosine of A is the reciprocal of the sine of A? Well, maybe your picture helps, maybe it doesn't. The definitions of these trig functions might be helpful. So in a right triangle, the definition for cosine is adjacent over hypotenuse. That's what it means. That's what the cosine function does for an angle in a right triangle, adjacent over hypotenuse. Equals 1 over sine. Well, what is sine? What's the definition for sine in a right triangle? It is opposite over hypotenuse. And like I said over here, when you have 1 over something, that's just the reciprocal of it, okay? So we have 1 over opposite over hypotenuse. And you can either jump immediately to say, all right, well, what's the reciprocal of opposite over hypotenuse? Or you could say, all right, well, if I multiply this by hypotenuse over hypotenuse like this, well, my left-hand side stays the same. It's just adjacent over hypotenuse. That doesn't really change at all. And then notice on the right, I have this 1 times hypotenuse. That's my numerator is 1 times hypotenuse. Well, that's just my hypotenuse. And then my denominator is opposite over hypotenuse times hypotenuse. Okay, well, that means that those are going to cancel, right? Because one's being divided and one's being multiplied. And so my denominator there simplifies to opposite. Oh, and I should say this is a question mark, right? Like, is this true or not? That's the thing that we're trying to find, right? It's like, is this true or not? So now we've got this statement that's saying that adjacent over hypotenuse equals hypotenuse over opposite. And like, that doesn't really make sense. Like, there's a lot of problems with this. First of all, the hypotenuse is the longest side. And so adjacent over hypotenuse, this value here is less than 1, right? Because the numerator is smaller than the denominator. The hypotenuse is larger than the adjacent, and so this is less than 1. Whereas the right-hand side, I've got hypotenuse over opposite. Well, again, the hypotenuse is the longest side, so this is greater than 1. So there's no way that a number that is less than 1 can be equal to a number that is greater than 1. And so this has to be false. This is not a true statement. There are other ways of proving that this is false. What you could have done, actually, is just looked at basically any of the problems that we've done in this assignment so far, and you could just plug in those specific numbers, right? So if you wanted to plug in, maybe not this one, but if you go to number 6, right? If you look at, let's say cosine of b, and compare that to the sine of b, right? If you compare those values, well, if you flip sine, you get 17 over 8, and 17 over 8 does not equal 15 over 17, right? 17 over 8 does not equal 15 over 17. That is not a true statement. And so because that's not true, the statement for the question that we're doing right now, number 8, that has to be false. Because it didn't work with number 6, and it wouldn't work with any of the other problems. So you could have also done that to sort of prove that number 8 is in fact false. Number 9. Number 9 is asking, all right, well, tangent of b, is that the same thing as the tangent of 90 minus a? Maybe sketching a picture helps. I don't know. Couldn't hurt. It's like if you don't know what to do, you could try sketching. Call this A, call this B. So, we're dealing with both angle A and angle B in this scenario, so I wouldn't go ahead and label, opposite, adjacent. I mean, I guess we could label the hypotenuse, because that doesn't really matter, but this isn't really a problem where you want to be labeling opposite and adjacent, because this problem deals with both angle A and angle B, and those have, different opposite and adjacent sides. So, can't really add much to our picture here. What I think everyone in this class, I'm hoping everyone in this class knows, is that the measures of all three of your angles must sum to 180 degrees, right? That is true for any triangle on a flat surface. They always sum to 180. So we can say the measure of angle A plus the measure of angle B plus the measure of angle C must equal 180 degrees. Right? That is true for any triangle on a flat surface, and we're definitely dealing exclusively with flat surfaces in this class. So all three of those things add up to 180. Well, we don't know the measure of angle A, we don't know the measure of angle B, but we do know the measure of angle C. Angle C is a right angle. So measure of angle A plus measure of angle B plus 90 degrees, because that's the measure of angle C, equals 180 degrees. Let's get our constants on one side of the equal sign. So that tells me now that the measure of angle A plus the measure of angle B sums to 90 degrees. By the way, this also tells us that A and B are what are called complementary angles, because complementary angles sum to 90 degrees. Just like supplementary angles sum to 180 degrees, complementary angles sum to 90 degrees. And in a right triangle, your acute angles are always complementary. They always sum to 90 degrees for this reason. All right. So we know that the two angles combined get us to 90 degrees. Well, notice that in this problem, we've got B and then we've got 90 minus A, right? So if we could maybe compare those things. If I take a look at my equation right now, well, I can see that if I bring A over to the right-hand side, I'm going to get something that looks kind of similar to the things that we're talking about here. So if I subtract the measure of angle A from both sides, I get the measure of angle B is equal to 90 degrees minus the measure of angle A. And if I sort of, maybe simplify this a little bit by maybe dropping some symbols, et cetera, et cetera, et cetera, basically what I'm saying is that B is 90 minus A. Right? I mean, I'd say that the way that I wrote it the first time is, quote, better. But, if you drop the M's and the angles and the degree symbols and you sort of just focus on the items themselves, I guess, objects themselves, you end up getting that B equals 90 minus A. Well, they're the same thing. So this thing is the same thing as this thing. And they're both tangent. So they're taking the tangent of the same thing. And so therefore, this has to be true. Because in my original statement that I'm trying to figure out, is this true or not, it's the same trig function, they're both tangent, and then the thing inside the parentheses, it turns out that they're equal. The measure of angle B is 90 minus the measure of angle A. So if B is, 50, then A is 40, and 90 minus 40 is 50. Right? If B is 10, then 90 minus 10 is 80, and 10 plus 80 is 90. So no matter what your angles are here, they're always going to sum to 90, and so therefore they're complementary, and so therefore this is a true statement. Number 10. Number 10, I'm not going to draw a sketch here because it actually turns out that it's not that helpful. So I'm just going to jump right to the definitions here. For number 10, we're dealing with tangent, cosine, and sine. And if you don't know what to do, try plugging in the definitions for these functions in a right triangle. The definition for tangent in a right triangle is opposite over hypotenuse. Times cosine, well, the definition for cosine is adjacent over, no, sorry. It was tangent, so it's opposite over adjacent. My bad. Opposite over adjacent. And then cosine is adjacent over hypotenuse equals and actually we're trying to figure out whether this is true or not, so put a little question mark over it. And then the definition for sine is opposite over hypotenuse. All right, so the question is this a true statement? Well, there's not a lot that we can do on the right, but notice on the left that we have an adjacent in the numerator and an adjacent in the denominator, and we're multiplying. Now, if we were adding our fractions, we could not do what we're about to do. But because we're multiplying, well, it just means that those cancel. Right? So when you're multiplying, if you have a factor in the numerator and a factor in the denominator, then you could just cancel them out, and this factor of adjacent is in both. So they go away. So the left-hand side simplifies to opposite. That's the only thing left in the numerator, and the only thing left in the denominator is hypotenuse. On the right-hand side, we had opposite over hypotenuse, and those certainly look the same to me. And so this is a true statement that if you take the tangent of an angle, and multiply by the cosine of that same angle, the product, the result, will in fact be the same thing as the sine of that angle. And this is a proof showing why that's true. All right, number 11. For 11 through 13, use a trig equation to find the unknown side. Round values to the nearest tenth. Round values to the nearest tenth. Number 11. We have a right triangle here. We know, obviously we know the right angle. We know one of our acute angles. We know one of our sides, and we are looking for another side, and then a third side is not labeled at all. So this is kind of a classic right triangle trig question. You're going to definitely want to make sure that you know how to do this because it's not going to go away. You're going to see this next year in Math 3. You're probably going to see it in pre-calc and calc and all this other stuff. So if this is your first time seeing this kind of problem and you don't understand it, that's perfectly fine. But please do understand that this kind of stuff is not going to go away, and so continue to practice this until you feel comfortable with the material. Because like I said, this is a classic right triangle trig question, and you'll have plenty of opportunities to practice this. So we're looking for A. We solve for A and we're done. And they gave us one of our angles. Now, without too much difficulty, we could, if we wanted to, we could solve for the other angle, right, in the top right. In fact, it's 55 degrees, right? Because 55 plus 35 is 90, plus another 90 gets us to 180. So you could solve for the missing angle, but it's not really necessary in this problem, because in this problem, let's just deal with the 35. Okay, let's just orient our minds, or sort of label this triangle in regards to the 35 degrees. Well, 16 is my hypotenuse, no matter what. The blank side is opposite. And the side that has A, which is the thing that we want, is adjacent. And that's because we're talking about the 35 specifically, not the 55. We don't need to solve for that. We'll just stick with the 35. Now, the key to unlocking this problem, and arguably the most important part of this problem, is we got to ask ourselves, all right, which trig function, right, sine, cosine, or tangent, which trig function connects the thing that we know with the thing that we want to know. Okay? And there's only one right answer here, right? It's either sine, cosine, or tangent. Okay, one of those is correct, two of those are incorrect. And we say, based on the things that I've circled in green, which trig function, sine, cosine, or tangent, deals with both adjacent and hypotenuse. So I would encourage you to think about that for a second. Pause the video if you need to. Ask yourself which trig function deals with adjacent and hypotenuse. And hopefully you came up with the correct answer, which is that the trig function that deals with adjacent and hypotenuse is cosine. If you said sine or tangent, I'm sorry, but that is incorrect. We need to use cosine with this problem, unless we solve for the 55, in which case we're going to use sine, but that's just extra work, so let's not do that. So it's cosine. Now, the cosine function is of an angle, right? So don't say like the cosine of 16. Like that doesn't make any sense, right? 16 is a side. You're not going to take the cosine of a side. You're going to take the cosine of an angle. And the angle that we're dealing with here is 35 degrees. So it's cosine of 35 equals. What is the definition of cosine? Well, if you were able to identify that cosine is the correct trig function here, you probably also know that the definition for cosine is adjacent over hypotenuse. So now what you got to do is you got to plug in whatever, letters and numbers represent those things. So cosine is adjacent, which in our picture is labeled as A. It's the thing that we want to know, over hypotenuse. And my hypotenuse is the thing that we're given, which is actually 16. And so now what we have is we have an equation that we can now solve for A. It's like we're done with the picture, right? We no longer need the picture. Now all we got to do is we got to get A by itself, and then that's our answer. A is going to equal something. Well, the only thing preventing A from being by itself is that 16. So if I multiply everything by 16, I'm going to flip it around. So I'm going to have A on the left here equals. Now I have cosine of 35 degrees times 16. I would strongly encourage you to put the 16 first. Technically, it's not necessary. Technically, you could say cosine of 35 degrees times 16, but trust me on this one, and I hate when teachers say trust me, but trust me, trust me that you're going to want to put the 16 in front. It's just going to make your life easier down the road. So just get in the habit of doing that now, and don't develop habits that are going to make your job harder when you get to more complicated problems. Put the 16 in front. So it's 16 times the cosine of 35 degrees. 35 degrees. All right? Now, that is an exact answer. 16 times cosine of 35 degrees, that is A. And that's about as exact as you can get, and you can't really write this in a different way and have it still be an exact answer. Now, the directions did say round values to the nearest tenth, so we do not want to leave our answer like this. We want to say that A is approximately something, right? And so in order to figure out what that something is, we're going to have to bust out a trig calculator, a calculator that has the trig functions in it. So we'll go ahead and take a look at that right now. We want 16 cosine of 35 degrees. Now, you may or may not have the same model of calculator that I do. This is modeled after the TI-84 plus CE, which a lot of you have, but not everyone. Regardless of what calculator you have, it is going to be absolutely vital that your calculator that has trig functionality, is in what's called degree mode. If you have the 84 plus CE, there's these words here at the top: normal, float, auto, real, radian, MP. The issue is this radian, right? So again, depending on the calculator that you have, you might not see this at the top of your screen, and that's fine. But if you do have this one, you'll see that it says radian. That's a problem, because right now your calculator is in radian mode. So regardless of what kind of calculator you have, you should press mode, which is up here next to second. And again, depending on which calculator you have, your screen might look slightly different than mine. But what matters is where it says radian and degree. Okay, so for me, that's like the fourth line down. Radian and degree. And you can see that radian is currently highlighted. That's no good. I want degree. So what you got to do is you got to go over to degree and then press enter. And now notice a couple things. First of all, notice that degree is highlighted. Notice that radian is not highlighted. And if you have this exact or something similar calculator, you'll notice that at the top of the screen, the word radian changed to degree. So now it tells you that your calculator is in degree mode. If you don't have these words at the top of your screen, you have to go into mode and double check and see is degree highlighted or not. So if you have like a TI-83, which is what I had in high school, we didn't have these words at the top of the screen. So you have to go into mode and you have to make sure that your calculator is in degree mode. If it's in radian mode, you will get the wrong answer. Okay, there's no other way to put it. So you can press second mode to quit. Okay, so quit is in blue. So second mode quits back to the home screen. And we want 16 cosine of 35 degrees. And it's a good habit to get into closing the parentheses. In this case, it doesn't technically matter. You'll still get the correct answer if you don't close the parentheses. But again, sorry about that, cut out for a second. If you, it's a good habit to get into, and we want to build good habits sort of when we're dealing with more elementary problems before we get into more complicated things. So you should close the parentheses, press enter, and we end up getting 13.1. And so getting back to my answer here, we end up getting 13.1. And we don't have any units here, so we're just going to leave it as 13.1. And that is my answer for number 11. Number 12. So number 12, same directions as before. We have a right triangle. One of our acute angles is 73. One of our legs is labeled as B, and our hypotenuse is labeled as 7. Again, we could get the other acute angle without too much difficulty, but let's just stick with the 73. 7 is my hypotenuse no matter what I do. And in regards to the 73 degrees, B is opposite, and my blank side is adjacent. And the question becomes, which trig function, sine, cosine, or tangent, connects the thing that I want to know with the thing that I already know? Right? So sine, cosine, or tangent, which one deals with both hypotenuse and opposite? I would encourage you to pause the video if you don't know the answer and try to figure out, is it sine, cosine, or tangent? Because there's only one correct answer here. And for number 12, it turns out that the trig function that deals with hypotenuse and opposite is sine. So if you're using the 73 in this problem, you got to use sine. If you want to solve for the other acute angle, it's 17 degrees, in which case you use cosine. But we're going to stick with the 73. Sine, the sine function is of an angle, so it's 73 degrees. That's the angle that we're talking about. The definition for sine is opposite over hypotenuse. In this case, opposite is labeled as B. It's the thing that I'm trying to find. And my hypotenuse is 7. And now we're basically done with our picture, and now I just need to get B by itself. The only thing preventing B from being by itself is the 7, so it's going to look very similar to 11 at this point. The process will. I'm going to take everything, multiply by 7 to clear out my fraction and get B by itself. I'm going to flip it around, so B's on the left. And just like I said with number 11, I strongly encourage you to put the 7 in front. So 7 times the sine of 73 degrees. That is my exact answer, and I can't really write it in any other way and for it to still be exact. The directions did say to approximate our answer to the nearest tenth. So we're going to go ahead and type it in. Notice our calculator is in degree mode, and we're go to mode to just double check. Yep, still in degree. Great. Second mode to quit. 7 sine of 73 degrees, close parentheses, and we end up getting 6.7 when we round to the nearest tenth. So our answer here is 6.7. And again, there's no units, so we're just going to leave it as 6.7. And that is my answer for number 12. I forgot to do this for number 11, but notice that you can check your answer by saying, all right, well, the hypotenuse is always the longest side, so my answer has to be lower than 7, in which case it is 6.7. I mean, it's close, but it's definitely lower than 7. If we had gotten an answer that was larger than 7, that's a problem, because it would mean that one of our legs is longer than the hypotenuse, which cannot happen. So you have to get an answer here smaller than 7, and 6.7 is close, but it is definitely less than 7, and so our answer makes sense. Question number 13. For 13, we are, again, given one of our acute angles. We're given one of our sides. In this case, it's a leg. And we're solving for x, which is another leg. I recommend that you just stick with the angle that you're given, which is 65. The blank side is always the hypotenuse. And, when I say, I mean regardless of what angle you're talking about in this problem. So the blank side's the hypotenuse, and opposite the 65 is what's labeled as 20. And the x, the thing that we're looking for, is the leg that's adjacent to my given angle of 65. Just like the last two problems, you got to ask yourself, all right, which trig function, sine, cosine, or tangent, deals with opposite and adjacent? And there's only one correct answer here. And that correct answer, pause it if you don't know it, try to get an answer, is tangent. The tangent function, the definition for tangent is opposite over adjacent. It's the only one that doesn't deal with the hypotenuse. The tangent function is of an angle, so it's 65 degrees. The definition for tangent, like I just said, is opposite, which in this case is 20, over adjacent, which in this case is labeled as x. Now, unlike the last two problems, unlike 11 and 12, with 13, the thing that we're looking for is now in the denominator. So we kind of have an extra step here. In order to get x by itself, well, first of all, x is in the denominator. That's no good, right? When the thing that you're solving for is in the denominator, you kind of have to you have to somehow move it into the numerator. You're not gonna solve for it when it's in the denominator. So to get it out of the denominator, you can just multiply the whole thing by x. All right? Because what's going to happen is it's going to appear on the left-hand side. It's going to appear right there, x times tangent of 65, because that's what we're doing. We're multiplying everything by x. And then on the right, your x's cancel because you're multiplying by x, but you're also dividing by x, and so they go away, and you're left with just 20. All right, so we've made some progress because x is now, at least now it's no longer in the denominator, but it's still not by itself. You want to get x equals, and it's being multiplied by the tangent of 65. Well, to get x by itself, you want to get rid of the tangent of 65, and because you're multiplying, you can get rid of it by dividing. Those are inverse operations. So we divide the whole thing by tangent of 65, and on the left-hand side, it cancels, and we're left with x equals, which is great, because that's what we're looking for. We're looking for x equals something. On the right-hand side, we've got 20 in the numerator, and then that's being divided by the tangent of 65 degrees. And that is our exact answer. You cannot get a more exact answer than that. You also can't really write it in like a nice, neat way unless you're going to approximate it. The directions did say to approximate this, to not give an exact answer. So we once again go to our calculator, and this time we're going to say 20 divided by the tangent of 65. Good idea to close the parentheses. And rounding the nearest tenth, we get 9.3. And so we end up getting 9.3, which is our answer. Now, this problem did not deal with the hypotenuse, so it's harder to check our answer. However, if this picture is drawn to scale, and it looks like it is, x certainly looks smaller than 20. So it's not as easy to check your answer this time because the hypotenuse is always the longest side, but this question didn't deal with the hypotenuse. But this picture is drawn to scale, and so clearly, if it is drawn to scale, then x is clearly shorter than 20, and 9.3 is shorter than 20, so our answer checks out, and that's our final answer.